Okay, let's take a look at the classic ladder problem. So you have a ladder leaning up against a wall. The wall has coefficient of static friction mu2, the floor has coefficient of static friction mu1, and we want to find the maximum angle at which we can lean this ladder and have it not slip and fall to the ground. So we want the ladder to be in static equilibrium because we don't want it to be moving. So that means that the sum of the torque on the ladder and the sum of the forces on the ladder both have to be 0. So we have these two conditions. And let's say we set up regular old axes, y and x parallel to the floor. So the first thing to do is to draw all the forces on the object at the point where they act. So this ladder has some mass, so at a point, the center of the ladder, we should have force of gravity acting on the ladder. At the floor, we should have a normal force perpendicular to the surface, so this is normal 1. And if the ladder were to slip, it would move this way, so friction must be acting in the opposite direction to keep it in place. So this is force of friction 1. On the wall, we have a similar thing. Now the normal force is going to point out this way, and the force of friction will point up, because if the ladder were to slip, this would fall down. So the force of static friction is keeping it up in place. And that should be all the forces that are acting on this object. Okay. So let's start with the torque. So I think I get to choose my pivot. So I think I will pick my pivot to be here, and we'll see what happens. So I'm going to pick my pivot here. So when we're summing the torque then, these two forces won't exert any torque. The torque will be 0 because they're at the pivot point, so the R associated with both those forces is 0. Remember that the torque, the definition for torque is R times F perpendicular, or RF sine theta, or however you want to remember it, R perpendicular F, whatever. So the torque is 0. So now we just need to add the torque from these three forces. So let's start with Fg. So Fg is a distance, this is L over 2 from the pivot, if the whole ladder has a length L. So we have L over 2, that's our R, and now we need the perpendicular component of the gravitational force. So when I look at this force, I can see that this line is parallel to this, so this is alpha. So if I want the force perpendicular to the ladder, or to the lever arm, I need to use the sine of alpha. So we will put Fg sine alpha. Now, should this torque be positive or negative? Well, let's say that counterclockwise is positive. So this would rotate the ladder around the pivot in a clockwise direction, so this should be a negative torque. Okay, now let's do N1. So N1, this is going to give us a counterclockwise rotation, so this is going to be a positive torque. The distance from the pivot to the point where the force is applied is L. The force is that normal force, and we need to figure out what angle we have here. So this angle is alpha. So the perpendicular component is again sine alpha. Okay, now this last friction force, F1, that's going to give us a clockwise torque, so it will be negative. It's a distance L, force is F1, and now we need to figure out the angle. So here, if we draw this little line here, so this is a right triangle, which means that this angle right here isn't alpha, it's 90 minus alpha. So that means that this angle is alpha. So to get the perpendicular component of f, we need the cosine of alpha in this case. Oops, and I put a theta there when I meant an alpha. There we go. Okay, so let's see. So first of all, we can see that the L's will cancel, so let's just get rid of those for now. And then let's see if we can substitute anything for these forces. So we have minus 1/2. This is the mass of the ladder times g sine alpha. And we're going to add the normal force from 1. We don't know what that is yet, so let's just stick it in there. And we're going to subtract, so F1 is a friction force, so that's going to be the coefficient of static friction here on the floor times the normal force on the floor times the cosine of alpha. Okay, so that's our equation from torque. So it has two unknowns in it. It has the N1 and it has alpha. So we need more information. So let's try, we did the torque, let's look at summing the forces. So let's start by summing the forces in the y direction. So if we sum the forces in the y direction, they should be equal to 0. So 0 equals, so what forces point in y? F2 points up, we have to subtract Fg, and we have to add N1. So again, F2 is the friction force here on the wall. So that will be mu on the wall times N2 minus mg plus N1. Okay, so this equation comes from summing the forces in y, and we have two unknowns here, N2 and N1. So we still need another equation because this one doesn't show up here either. So let's sum the forces in x. So in the x direction, we have N2 and F1. And F1, again, is mu1 N1. That's it. So that's our third equation. So we have three equations, and we have how many unknowns? We have N1, we don't know N1, we don't know N2, we don't know alpha, but we have three equations, so we can solve for all three. So we want alpha. So let's start by solving this equation for N2. So I'm going to do this in another color. So this will give us N2 equals mu1 N1. So I'm going to use this equation and substitute it in here. So here I'll get 0 is mu2 times N2, but we just solved for N2. We said it was mu1 N1 minus mg plus N1. So now I can add mg to both sides, and I could factor out an N1 here. So that will give me mu1 mu2 plus 1 times N1. And that, if I can solve for n1, n1 is mg over mu1, mu2 plus 1. So now that I've got n1, I can take n1 and plug it in here where n1 appears. So I'll take this equation, and before I substitute in for n1, I'm just going to move this to the other side and factor out an n1 on this side. So I should have half mg sine theta moved over here to the left, and then I'm going to factor out n1, and inside that we're going to get sine alpha minus mu1 cosine alpha. Now I can plug this in for n1. So this side will be the same. And here, mg over mu1, mu2 plus 1 times sine alpha minus mu1 cosine alpha. So I'm running out of space. I'm just going to rip that off there. Keep going. So here we can see that the m will cancel with the other m, and g will cancel. And what are we after here? We're after alpha. Okay, so we have alphas on both sides, so I'm going to take this side and divide by sine alpha. And I'm going to move this over to the other side also. So this side will become 1/2 mu1, mu2 plus 1. And this side will become sine alpha minus mu1 cosine alpha over sine alpha. And that, if we divide this into both terms, we'll have 1 minus mu1 over the tangent of alpha equals half mu1, mu2 plus 1. Okay, so now we just have to solve for tan alpha and we'll be done. So I'll switch this term with this term. And this should be negative here. Okay, so I just added this to both sides and subtracted this from both sides. And now we just flip it around. So mu1, we're going to divide both sides by this and multiply both sides by tan alpha. And you can see over here, if we distribute this half through, we're going to get minus half mu1, mu2 minus a half. So we're going to get 1/2 minus 1/2 mu1, mu2 equals tan alpha. And then finally, you could just multiply the top and the bottom by 2 here. So you get 2 mu1 over 1 minus mu1, mu2. And then you just take the arctan of alpha and you're all set.